All right, recording is rolling. Welcome to Tuesday, October 12th. Oh, yeah, we're coming back from a 3-day weekend. You guys have a good 3-day weekend? Yeah. All right, nice. All right, so, do you guys just pick up your new Open Notes take-home quiz from the front of your desk? It looks like this. All right, make sure it's the one that says AP. Has this picture on the front. You guys see that one? All right. Speaking of this take-home quiz, all right, I need to tell you guys a detail about this. So flip over on the back side to number 6. You guys see number 6 says 2 asteroids? Okay. So the picture that goes along with this didn't print out very well. So here's what it should look like. Well, might be able to trace the ink that barely made it to the page there. Is that? Right. So it's 2 asteroids, same radial size, spherical. They're just touching at the surface. Okay. Right, so that's that. Okay. Right, so here's the plan for the week. You guys remember we've been working on centripetal force and gravitation, doing a bunch of textbook problems. There was a main set that I assigned to you guys, so we're gonna finish those today. Take you guys over this. Now, tomorrow, you guys know the PSAT is going on, PSAT. Okay, so if you still have a question where you're supposed to be, then let me know. I've got an Excel file. This room is going to be used for the PSAT. You may have noticed because I took down all the posters. Looks like the Grinch has been in here over the weekend. He came here for all the physics posters. That's what he wanted. Left my room all bare. So tomorrow, if you're not taking the PSAT, are you going to meet here? No, you're going to. Oh, you got the 5th period. So what's the first place you guys going? Lunch. Yeah, and then go to 4211. You guys write this down in your planner somewhere? Okay, so you guys write that down? 4211, that's Miss Lewis's room. Okay. Okay, and then my original plan today was to do AP Classroom Unit 3, but I realized I forgot to remind you guys back on Thursday and Friday to do that. So we're going to bump that to Thursday. I'll let you open a couple more days. Okay, so if you haven't done that yet, I had about half the students finish that. So if you haven't done that yet, then do that next couple days. We'll go over that on Thursday. Okay. You guys are using those planners, right? You guys are using agendas. If not, then well, better late than never to start right now. So you guys got a room to go to. You guys got this assignment, and then the textbook problems we're going to finish today. I guess if you want to turn them in by the end of today, you could because you should all be finished. But I'm going to pick that up by Friday. So then I'll pop that right in the grade book. Okay. There's other stuff I do want to do with you guys. I've got a turntable lab. Always got FRQs, so I'll see what I can fit in these 3 days. You guys good with what we're doing? All right. So let's check this out. Next problem is number 56 from your book. This is by number 50. This one right here. So zoom in. Show that the escape speed from the surface of a planet of uniform density is directly proportional to the radius of that planet. Woo! So some kind of proof that there's no numbers. So just for what in general, any planet, so any planet that the required escape speed would be proportional to the radial size of that planet. So zoom back out. Well, let's think about how we could approach something like this, 56. Maybe first I'll start with a picture, try to get an idea on what this could mean. Okay? So you might have a planet, has some radial size, maybe like r, okay? And you're trying to send a rocket. You guys remember what escape speed means? It's like how fast you have to get this rocket going so you can cut off the engines and it can still escape the planet. Get away from her. Okay? But then what if you start pumping up the size of this planet? So maybe like this big. How fast would it take for that rocket to escape the planet? Or what if you blow up the planet like this big? Okay. So as you're making this radial size bigger, 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 okay. Do you think it would take more and more speed to escape that planet?
I think so.
Makes sense, wouldn't it? Yeah. Uniform density. Let's say these are all the same size or same material, like same dirt, whatever. Okay. I mean, if it was a little tiny asteroid, it'd probably be pretty easy to escape from it. Right? Bigger the planet. Now, here's where and then let's get the escape speed. formula. So this is something that I'll actually derive for you guys in the future using conservation of energy. So your textbook order and how I'm used to teach in this class is different from AP order, but so there's a few topics that are a little bit out of order. So I'll be right. So somebody did this, right? Now, as this radial sizes get pumped up, you guys said, well, it makes sense you would need a greater escape speed, greater required escape speed. Okay? But at a glance, it looks like this formula might be saying the opposite. Because as you pump up this R bigger, 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 doesn't that look something to do like inverse type relationship? Like you actually need a smaller speed? Wait, how is that? Who sees how? And that looks like a contradiction, doesn't it? What else? Hey, how about this? As this radial size is getting bigger, 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 if there's uniform density, then is something else in this equation also changing? The mass. The mass. In fact, you know what? I bet the mass changing would have a greater effect than the radial size changing. And for that, I have to tell you guys about scaling. So, scaling. Suppose you had a little box, a little three-dimensional box. Let's say it's like 1 unit by 1 unit by 1 unit, something like that, 1 by 1 by 1. Okay. So I'm going to blow up this box bigger. I'm going to make it, let's say 3 by 3 by 3. So I'm going to increase it by a factor of 3 in each dimension. So 3 times as wide, 3 times as tall, 3 times as far back into the page. Maybe it's a transparent box, a little easier to see. Like this going on? Well, there's the floor tiles anyway. Hey, how many floor tiles do you guys see? 9 floor tiles? You guys see that? Huh. Which makes me think, if there's a linear expansion, by a factor of 3, then how does the surface size change? The surface area expansion. And later on, maybe like volume. Okay. So if you blow it up by a factor of 3 in a single dimension, right, you guys just told me what happens to the floor size. The floor size went from 1 tile to 9 tiles. Hey, isn't that kind of like 3 squared? In fact, you know what? If linear is like 3, that's like 3 to the 1. And then anything to do with area, area is like 2 dimensions. Okay. Do you guys think what about if you were to paint the little box, and then how much more paint would you need to paint the big box? You guys think it would take 9 times as much paint? Right? Because, hey, surface area, that's like an area relationship, right? What if you fill this box with water? So you fill the little box with water, it takes like, so much water. How much more water would you need to fill the big box? That's a cube relationship, isn't it? So it's a factor of 3 to the power of 3 because 3 dimensions. That's like 27 times. Okay? So whatever the scaling factor is, anything to do with area is the squared version of that, and anything to do with volume is a cube version of that. Okay? Which is about to tie in back to that question that we're working on, because doesn't mass occupy volume, right? So if something's getting bigger, 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 right, then yeah, sure, this radial size is getting bigger, but the mass is getting bigger too, and because the volume is getting bigger. Right? Let's get an expression for mass in terms of like radial size, something like that. Okay. Wouldn't maybe I'll change ink color here. Okay. So isn't mass equal to density times volume? Okay. So mass equals density times volume. Right? Isn't that true? Okay. And isn't volume something? Isn't it proportional to r cubed? Right? If you assume this is a sphere, it might even be Does anybody happen to know the volume of the sphere?
Wasn't it like 4/3 pi r cubed?
Yeah. You guys got it.
Yeah.
Yeah, there you go. Okay. So what I can do is I can take this whole expression right here. Like mass of planet in terms of some uniform density. Like it's all like some space dirt. And multiply by its volume, which is this expression in terms of its radius size, I can just substitute that right in there. Let's see where we're going with this. So escape speed is equal to square root of 2g times 4/3 pi r cubed and this is all divided by r. Oh, hey, is one of those r's going to cancel? Yeah, so this one goes away entirely, and this one drops from 3 to 2, the power, right? Kind of r times r times r on top, and just an r on bottom, so one of those cancels. Okay? That's going to leave you, oh, and I have r squared inside the square root. Hey guys, what's the square root of r squared? That's just r. So escape speed is equal to this giant square root here. Got 2, well, okay, 2 times 4/3, that's like 8/3, isn't it? So 8/3. I got a g. I got a pi. All times, we're done square rooting. R. So that very last line, you could say then that escape speed, kind of cram this in, that's why I'm changing heat color, is directly proportional to the radial size. Because 8/3, square root of 8/3 pi times g, this is all a constant. You guys see that? All square root stuff is just a constant. Oh, I forgot my row. Do that last class too. Okay. You guys see this this row right here? I need a row right here for the density of the dirt. Okay, just throw it somewhere in there. That's all out of order. Okay, is that okay? All right, now this actually reminds me of a story that I told you guys last week. Actually, I was referencing that problem sort of. Do you guys remember the story of we're tunneling down into the center of the Earth, and then we turned around, took off in a rocket, and we're looking at your weight relative to like different locations. Okay. So you put weight as a function of radial distance, and here's a very special radial distance. That's the radial size of the planet. Okay. I should draw you guys a picture again. Okay. So if you're standing at the surface, you have some weight, okay. And then I might call it mg, or well, maybe even better, gmm on r squared. Right? Then what if you tunnel down into the center of the Earth, do the spiral staircase, and then right at the center, what's your weight equal to? 0, because every grain of sand pulls you a different direction. It all cancels out, floating around like an astronaut. Okay, okay, so that point's there, that point's there. I know if you take off in a rocket, as you get further and further away, your gravity pull from Earth decreases. There's an inverse square relationship, so it goes down. Okay. But I told you guys that if you climb the spiral staircase all the way down to the center, that your weight decreases proportional to how far you are from the center there. Okay. So if you're halfway down to the center, like right here, then you would weigh half as much as you would at the surface. Okay. And I was thinking your textbook asked you that question, but let's go do that. I want to prove to you guys that this is a direct relationship. You guys ready to prove that? Okay. So isn't your weight equal to gmm on r squared? Right? That's your weight. Right? Maybe that's what this should be. This is gmm on r squared, where we're using capital R. I mean, it's a little mg2, but short for that one. Okay. But hey, look at this mass right here. That's the mass of the planet, isn't it? Okay. And remember how, as you go down, remember that whole story about like the eggshell planet? If you're inside an eggshell planet, all the mass above you and elevation cancels out. So there's like a series of shells. Right? So effectively, the only part of the planet that's pulling you down is just everything beneath you in elevation. So your weight is equal to G times, okay. So for the mass of the plant, let's do the same thing we did before. Density times volume. Right, so density, like density of the dirt, times volume is 4/3 pi r cubed. We got your own mass, all divided by r squared. Okay, guys good? I'm not, that looks, man. But this looks like junk today. Okay. Weight is equal to, so GMM on r squared. Yeah. Just gonna rewrite this so it looks a little prettier. G times, okay, so mass, you guys know is density times volume. 4/3 pi r cubed. Yeah, is that what I said? Yeah. Times your mass, okay, all divided by r squared. Okay, that's your weight. It's like the gravity force on you. Okay, so good so far? Okay. What's gonna cancel?
R squared.
Yeah, the r squared, and then this reduces to 1. So it's r times r times r, all divided by r times r. So left with 1 r. Okay. So your weight, say the gravity force on you is, well, what have you got left? I got a gravity constant, I got the density of the dirt, I got 4/3, got a pi, I got your own mass, I'm gonna slide over here. And then multiplied by, there's only 1 r left on the board. I'm gonna slide that to the end. And the reason I'm writing it that way, I swapped this m and r, is because all the stuff in brackets, well, let's see, universal gravity constant, we got some density, we got 4/3 pi. Aren't those all constants? And if your mass is also constant, this whole expression, everything in brackets, all the bracket part is constant. Right? Hey, does this look like y equals mx? Y equals mx. That's exactly what that looks like, doesn't it? And your x value would be radial distance, and your y value is like your weight. Oh, that's exactly this graph, isn't it? If your weight is a function of your location from the center. So all the stuff in brackets represents what aspect of this graph? The slope of this line. The slope of this line, slope, is equal to all that stuff. There's a g, there's a rho, there's a 4/3 pi, and there's your own mass. Okay. There you go.
So is that like, what's the answer? Like,
Oh, so just the fact that this takes the form of like y equals mx, where here you can say this. You say weight is proportional to r, right? So weight is directly proportional to r because it just takes that form. Okay. That actually wasn't one of your textbook problems, but I wanted to do that one anyway with you guys. Hey, that could be an FRQ one day, possibly. It may. Could happen. All right. Let's see, what else I got lined up for you guys? Number 75. 75. In a popular amusement park ride, a rotating cylinder radius so many meters is set into rotation at an angular speed of so many radians per second, as seen in this figure. So zoom, 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 zoom. Now, angular speed, that's a concept I just taught you guys back on Friday. It's like a spin rate, like how fast is something spinning. That's when we're breaking out this turntable, spinning this thing. Okay. So it's got maybe so many revolutions per minute, or in this class we're doing like radians per second. Some term per time. The floor then drops away, leaving the rider suspended against the wall in a vertical position, just like in this picture. What minimum coefficient of friction between a rider's clothing and the wall is needed to keep that rider from slipping? That would be the only force holding them up, wouldn't it? It would just be the friction force. It would be prevent them from falling. Yeah. So, yeah, don't wear wax paper clothing on that day. I think I'm gonna start this with a free body diagram. Maybe throw down some equations and see where this is gonna go. So, got this thing spinning. Well, let's look at like a slice of this. So this person's against the wall. Right? There's some radial size here. Call that R. This person might have some mass M. And let's look at some free body diagram forces on this guy. Okay. So as this thing is spinning, right? That's an important aspect. So this thing is spinning at some omega value. What's one force on this guy?
Gravity.
Yeah, his own weight, gravitational force, straight down. I'll call that mg. Okay. What's another force? Yeah, normal force. Which way does the normal force point? It's the force from the wall. Yeah, it doesn't point exactly inward. Okay, I just started drawing this picture 3D. You guys can think of 3D, right? Okay. So, wouldn't the normal force be pointing exactly towards the center of the circle? I'll call it normal force, center of the circle. Okay. If you're drawing your own and you don't like drawing 3D, you just draw it straight to the left. But, right. And any other forces on this guy? What's holding him up? Friction force, friction force. And the friction would be opposing, well, you would be slipping down otherwise, so friction force must be pointed that way. There you go. That's it. Those are the three forces on them. There's one force down, one force up, and one force pointing exactly into the circle, to the center of the circle. Okay. Where, of course, this is our right angle right here. This is a right angle right here. Got a couple of right angles there. Okay, now what do I know about, is this guy in equilibrium? Static equilibrium?
I think so.
Is he
Yeah, moving.
spinning around, right?
So is he like gonna be like pressed against the wall?
Isn't there a net force on this guy?
Net force of him going.
Yeah, and the normal force is acting as the net force. And isn't that also effectively the centripetal force? Right? So here's some things I know. I know that the normal force is acting as the centripetal force. So normal is acting as the centripetal force. And I also know some expressions for each one of those that I can substitute in. Okay? Like, force. Isn't normal force related to friction force through coefficient of friction? Right? But how about this? You guys know that friction force is equal to coefficient of friction times the normal force? I did this earlier today, and I had no problems doing it. I don't know why I'm having a brain slip right now. Check my stuff from earlier. 35. Force. Oh, okay. All right. Yep. I'm sorry, guys. I solved this a different way earlier. That was actually probably a little easier to solve. Okay. Let's come back to this idea. All right, so both those statements are true, but I'm going to start from a different spot. Okay. Actually, I want to start with this right here. So friction force is equal to coefficient of friction times normal force. Now, we'd be interested in static friction. Let's say it has to build up to some number. So we're looking for like a minimum friction value, right? Like that. Okay. And this normal force is the same thing as centripetal force. So I'm going to take this and substitute it like right here. Okay. So friction force is equal to coefficient of friction times normal force. But normal force is now, well, there's two versions of centripetal force. So I'll say F centripetal. Okay. All right. Now, centripetal force, the classic way you guys learned it was mv squared over r. You guys remember that? Mv squared over r. But your book told you something about omega, which is a spin rate. Does anybody happen to remember what centripetal force is in terms of omega?
Was it? I'm just going to my notes.
You guys remember?
Mass
Uh-huh.
omega squared times r.
Yeah. It's m omega squared times r. Yeah, there you go. Okay. So, if you forgot that, then you could just take this and substitute it in for v, like mv squared over r. So centripetal force is mv squared over r. Take this, sub it in, you can also get this. Centripetal force is m omega squared r. Yeah, exactly. Okay. You got that. And hey, the friction force, isn't that also equal to what? mg, the weight, right? So as long as the friction force can at least be as much as that, right, then you're good. So what's going to cancel on both sides?
Mass.
Yeah, you got mass. Okay. So what that means is that it doesn't matter if you have like some kid in there, some adult, or you have lots of different riders, lots of different masses. Right? Whatever the answer is to the necessary minimum coefficient of friction, it's going to be the same for everybody. Right? And actually, we're just one step away from getting that. You guys see what that is? So the minimum coefficient of friction is just G divided by omega squared r. Yeah. That's the answer in terms of variables. So that's a little messy, but well, your book gave you numbers, so you can just plug in the numbers. Yeah. You guys good? All right, there's one more that I assigned to you guys for your main homework. And I didn't realize this until after the fact, but this next one upcoming, number 76, actually involves some conservation of energy. So I'm going to introduce a few new ideas to you guys as we're solving this one. I'll take you guys through it anyway, but this is about some of the next stuff that we're getting into. So got a massless spring. You guys see this picture down here, right? Of some given spring constant is fixed on the left side of the track. A block of some given mass is pressed against the spring. You guys remember Hooke's law, F equals kx? Okay. That's sort of going to come back. Got to reference that. Some distance d, and then you let go, pew, and the block flies around track. They told you the radial size of this loop. The entire track is frictionless except for this segment AB. So this segment AB has a coefficient of friction, but everywhere else it's frictionless. Okay. They told you what the coefficient of friction is. Find the minimum compression D, like how much you have to compress the spring, compress that spring, to make sure that the block just barely gets around the loop. Okay. How much do you have to compress it as a function of all these other given values? Okay. This kind of makes sense if you don't compress it very much. Maybe the block gets like, gets about here and stops. Press a little more, it's like, and then it slides up here and falls back down. You compress it really hard, maybe it gets around with sufficient speed. But let's say, what's the tipping point where just barely gets around? Okay. So we're going to put some ideas together, including new stuff from the future. Yeah, that's all right. I'll take you guys through this. All right, so we got this track. Something like this. There's a spring with some spring constant. Got a block of some mass. We're going to compress this spring some distance d. Right? So the spring used to be this length. Right? And just went compress it. Right? Then that, the block's going to, from point A to point B, go over a rough patch, has some coefficient of friction. Right? And then it's going to wheel around this loop, which has some radial size r. Right? And yeah, what's the minimum compression to make sure that it gets around? Right? Now, I'm thinking that probably a critical point is this point right at the top. Right? So let's look at a free body diagram of this block by the time it gets to this point. So free body diagram on that block right there. Right? Now, it'll be in motion if it gets around. So some speed to the left, got some speed v. Right? If it gets around with sufficient speed, that's probably how AP would phrase that, like sufficient speed, then what forces would be on it? I mean, the block's got a weight, right? Call it like mg. or free body diagram force, right, mg. Okay. And if it's going around with sufficient speed, isn't there also a normal force from the track pointing which way? Also down, right? But we're not solving for sufficient speed. We're solving for the case that it just barely gets around. If it just barely gets around, do you think the normal force on the block would approach zero? So actually, this would be the entire free body diagram for the case that we're interested in. Okay. Got another question here, which is starting to be related to future content. Okay. What's the height of that circle in terms of its radius? 2r, right? Isn't height equal to 2r? Am I true? Right, now, why do you care about that height thing? Well, hold on to that idea, because that's coming back. Now, back to something that you guys are familiar with. Right? This block swinging around here, and the only force that's keeping it on this curved path happens to be its weight at that particular instant. Right? The normal force approaches zero at that point for this setup. Right? Wouldn't you say that the centripetal force is being provided by its weight? You guys would say that, right? Okay. And the reason I want to write that is so that we can solve for how fast does it have to go? Okay. And then we'll be able to use that and solve the rest of this. Okay. Oh, what's going to cancel out?
Mass.
Yeah, the mass of the block. So it turns out the mass of the block is, well, it does cancel out for this part. Now, later on, it might be important, but cross multiply bar, take the square root. You guys see as the minimum speed to get around would just be the square root of gr. Okay. Now hold on to this idea because that's an important middle step. Okay. Great, gr. Okay. All right. Now you guys ready for next week's type stuff? Okay. Next week we're going to get into a very important concept in physics called conservation of energy, which is actually one of the earlier chapters in your book, and that's why this is showing up here. Okay. Conservation of energy says that energy cannot be created or destroyed. Now, it's okay for it to transform different forms. And yeah, so energy take different forms, but the quantity is going to be conserved. Kind of like mass, like conservation of mass. You guys remember chemistry? You do all those chemical reactions, and the mass before equals the mass after. Right? Well, now we're going to go through some physical process and say that the energy at one point in the system is equal to the energy at the end. Okay? You guys remember doing all those kinematic problems, like a car brake to a stop? We said there's a beginning point, end point, or Galileo dropping stuff off a tower, or like a cannonball being shot, off the edge of a cliff. There was always some initial point and final point, just like there is here. And you know what? All those scenarios that I just named, like Galileo dropping stuff, or shooting cannonballs, or car braking to a stop, all those can also be solved with this new method that you guys are about to learn. And actually, it's even faster to solve all those problems with this new method compared to the old way. Okay? So energy can take different forms, right? So let's start to write down those forms. Let's do this for, and this is something that AP cares about too. We're going to look at the system. We'll call it a block Earth system. So block Earth. Okay. Block Earth system. Okay. Now, why do I care about block Earth system? I care about the block because the block itself can be moving and speeding up, slowing down, changing height. So obviously I care about the block. Okay. The reason I care about the Earth is because the block is actually going to change height against Earth's gravity, so you need Earth to be part of the system. Okay. And see as part of the track that is going to be slowing the block down, well, that's going to be taking some of the energy out of the system. That's how AP wants you to think of it. Okay. So here's what a conservation of energy setup would look like. Okay. Now this is not well. We're gonna start with some simpler ones next week, and then we'll build up to those. But here's what this one looks like. I think you guys will be able to get this because you guys are pretty sharp. Okay. Here's some energy stored in the spring. I'll say energy stored in the spring. Okay. Whatever that would be. And I'm about to show you guys what that is. Okay. Then when the block goes over this rough patch, it loses some energy out of that system. Now the energy doesn't disappear, but it leaves this system and goes into probably thermal energy or something. Okay. So I'll say minus work done by the friction. Okay. So you start off with all the energy in spring. A little bit's going to be going to seep out because of the friction. working by friction, and you'll be left with some energy over. Now that leftover energy better carry the block around this loop, right? Now here's where energy can take different forms. There's what's called potential energy. That's like energy of height. Ooh, maybe like if you're to lift, I think the higher the block goes, the more energy that's going into energy of height. Okay? And I'll say plus kinetic energy. Kinetic energy is the energy of motion, energy associated with motion. All these have formulas associated with them, by the way. We're about to do that too. Okay? So that this block better be in motion at the top, right? It better be going at least as fast. If it has to be going at least as fast, it's going to have energy associated with that motion, called kinetic energy. Okay, so we have energy that came from here, well, came from the spring. Some of it was zapped out by friction. You have some energy left over, which is what has to carry the block up, and it better have some left over to be going at least as fast. Okay, you guys get that? Okay. Now, what are the formulas for each one of these? The one I do want to show you guys is the spring energy, and the other one, just take my word for it, and I'll show you guys those next week. Okay. So there is something that you guys know about a spring. And what you guys do know about a spring is Hooke's law. You guys remember Hooke's law? F equals kx. Or some textbooks say negative kx for whatever, right? So force in newtons versus spring compression, like how much you've compressed the spring. As you compress it more and more and more, it doesn't take more and more force to push it. Right? Or stretch it for the matter, that might be stretched. So stretch or compress. Okay. But remember how it ends up being a direct relationship with slope k, like F equals kx, right? Isn't that what that would be? Okay. Now, something else that you guys have learned in this class about graphs is that graphs might have different properties that tell you different things. For example, a v versus t graph, speed versus time, doesn't just tell you about speeds. It can also tell you acceleration, that's the slope of the graph. It can also tell you displacement, that's the area underneath the graph. You guys remember that? And if you're ever not sure what you're getting from a graph, then look at the units, in this case like newtons and meters, the units of the axes, and it might tell you something. And I'll go ahead and tell you guys what the end result of this is going to be. If you look at the area under F versus X, so that triangle, okay, this area represents the energy stored in the spring. Because the units are consistent with that. Okay? So why is that? Because 1 joule, which is a unit of energy, breaks down into, it is a composite unit, just like the newtons. It actually breaks down into 1 Newton times meter. Okay? Which happens to be Newton meters. That's the area of that triangle, isn't it? Okay? So speaking of F equals kx, suppose that this distance is exactly x, and the corresponding force is, well, it would be kx, wouldn't it? Okay. What is the area of that triangle? Because it would represent the energy stored in the spring. So isn't that equal to 1/2 base height, because area of a triangle? So area of triangle is 1/2 base height. So that's 1/2. The base is x. This is x. The height is kx. That's what this height is, right? Kx, because F equals kx. Okay. Do you guys see that the energy stored in the spring is just going to be equal to 1/2 kx squared? Guess that? Okay. Okay. So this is a new expression. You guys will see this in the future. I'm not going to explain all these terms right now. You guys see this, but I just wanted to at least show you guys one of them. Okay. So let's go back to right here and put this together. Okay. So here's where the energy is coming from. Here's where it goes to. So start popping in formulas. So energy stored in spring, 1/2 kx squared. Okay. Now, some work is going to be done by friction. Isn't that coefficient of friction times the normal force on the block? Well, it should say it's force times distance is what it is. Okay. So the coefficient of friction, and isn't the normal friction equal to the weight of the block? So there's force, and then times distance that it acts over. So that'd be basically the length AB, right? And the leftover energy better do 2 things. It better lift the block to some height, Now here's the expression associated with this, mgh, which is also sort of a force times distance if you think about it. So we've got a force here, just in red ink maybe. This is a force. This is a distance. This, mg, is a force. H is a distance. Guess that? And 1/2 kx squared, well, that was sort of a force times distance too. It was just a variable force. So it worked out kind of funny, but it's the same concept. Okay? And then plus kinetic energy. Here's the formula associated with kinetic energy. It's 1/2 mv squared. Just take my word for it and then run with that. Okay, so that is the conservation of energy expression that would solve this question. That does also involve some rotational stuff, but we took care of that part already. And the question is, what's the minimum coefficient of friction? Or, I'm sorry, what was the question?
I thought we were solving minimum compression to get.
Oh, minimum compression. Yeah, thanks. Thanks, guys. Okay. So yeah, we're solving for this compression. Solve for that compression, right? Okay, thank you. Okay. All right. So it looks like what I got to do then is subtract this term over, and then divide by k, multiply by 2, take a square root. Okay. Actually, do you think you guys could finish this up? Yeah. So add this over. So 1/2 k times the compression distance squared is equal to mgh plus 1/2 mv squared plus mu mgl. Okay. Multiply by both sides by 2, divide by k, take the square root, and that would give you the compression distance. Is that, your book gave you values for all those, so you can plug them in whenever you want. Okay. I asked you guys a question about this on your take-home quiz. You probably saw your take-home quiz has the same picture. But it asked you about relationships. So if you take a good look at this and think, if I change one variable, how would that affect something else if everything else is the same? Then I bet you guys can use your critical thinking and figure that out too. Okay. Yeah, go ahead and finish this off. So x is equal to, say, multiply by 2 over k, the square root of 2 over k times gh half mv squared umgl. The whole thing.
That's amazing.
Okay. All right. I had a few other things lined up, but yeah. I think here's what we do. Last 2 minutes of class is get you guys started on the bonus stuff in case you wanted to do that. Yeah, at least another practice problem. And here's the number 20. It says a coin rests so many centimeters from the center of a turntable. The coefficient of static friction is some number, like 0.35 or something. The turntable starts from rest and then rotates with constant angular acceleration of some given value. You guys remember what angular acceleration is from Friday? So here's a turntable. Hey, I got a coin on a turntable. This is exactly the scenario, isn't it? So this is going to start going faster, faster, faster. The rate that it's speeding up spinning is alpha. The rate it's spinning itself is called omega. Okay? But if it's going faster, 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 at some point, I saw that coin slip off. At some point, that coin's going to slip off. Okay. And the question is, what period of time does the coin slip off the turntable? Well, they also ask under what condition does it slip off. The condition it will slip off is if the necessary friction force is greater than, the centrifugal force would be greater than the friction can hold it. Okay? Because the friction force is acting as the centrifugal force. But how much time would it take to slip off the table? Oh, figure that out. So number 20. Number 20. So I got this turntable. Got this coin. Maybe this coin has some mass. I'm going to guess the mass is going to cancel out, but we'll see how it plays out. There's some radial distance, the center, okay? And this thing's going to be spinning. Now I'll write omega for the spin rate. The thing is that omega is not constant. It's actually a function of time, right? So it's omega equals omega naught plus alpha t. And if it starts from rest, then doesn't it just boil down to alpha t? This is analogous to v equals at if something starts from rest. You guys remember if you drop something off a cliff, after 1 second it's up to 10 meters per second, then after 2 seconds, 20 meters per second, then 30, 40, 50 meters per second. Okay. Gains 10 meters per second every passing second. Okay. Free fall. Okay. That's analogous to this. Right? So this is like spinning. Right? How many radians per second? Okay. Here, this is radians per second. This is radians per second squared. And this is, of course, seconds. Like that. Okay, so we've got this. Okay. Think about free body diagram on this coin. Okay. Now, this coin has a centripetal force provided by a friction force. Okay. It's also got a weight down and a normal force up. So those are two other forces, but there's the friction force that's acting as a centripetal force. Okay. Okay. So I know that centripetal force is being provided by the friction force. Maybe I'll start there. Okay. And then think, okay, well, what values can I substitute into these and then solve for stuff? Okay. Well, centripetal force I know is mv squared over r, but I also know it's m times omega squared times r. Can that be true? Okay. And then friction force, isn't that coefficient of friction times normal force? But isn't the normal force just equivalent to the weight? Right, so a couple of substitutions there. Right. Good so far? Oh, what's going to cancel? The mass of the coin, which you probably were expecting anyway. We've done enough of these that hopefully you kind of feel like, okay, mass is probably going to cancel out. It does. Right. Now, omega is actually not a constant value. It's a function of time, isn't it? It's alpha times t. So let's sub that in. So alpha t squared r is equal to omega g. Okay. And the question is, how much time does it take before that thing starts slipping? Oh, well, can we just do some algebra and solve for t? That's it. I mean, if you got that far, then you can do physics, because the rest of this is just algebra. That's all the physics. We're done with the physics. So divide both sides by r. Alpha t squared equals mu g on r. Square root both sides, divide by alpha. So t is 1 over alpha times square root mu g on r. There you go. That's the answer to number 20. Oh, well, of course, your book gave you a bunch of numbers, but there it is in terms of variables, which you guys should be able to do. Okay. Let's think about what this would mean. How does this play out? So what if you were to go to a planet that had more gravity, like increase the gravity? Okay. Would it take more or less time for that coin to slip off? More time, right? Suppose you had 4 times the gravity field. Then it would take twice as much time before it slipped off, right? Because that gravity is really holding that coin down. Right? What about this? What if you increase the coefficient of friction? Would it take more or less time before a coin slipped off? More time. Yeah, if you had 4 times the friction, see it'd be double the time. Right? That kind of makes sense too, doesn't it? What if the coin was further and further out? Would it take more or less time for the coin to slip off? Less time. Hey, because that's an inverse relationship. But you guys already know that because you guys saw that back on Friday. Remember how if I have a coin near the center and a coin near the edge, zoom out here, okay, and I start spinning this, which one's going to fly off first? Yeah, it's got to be the outside coin, right? So that's to say the further out it is, the less time it's going to take before it flies off. If the inside coins, it's harder to make those move. So that's consistent with this equation. Okay. And then finally, what if you increased alpha? That's to say that the rate that you speeded up spinning is increased. Would take more or less time to slip off. Oh, also less time, wouldn't it? Yeah, doesn't this formula kind of check out? Makes physical sense. Guess that? All right, I'm gonna find you guys' VTV news, and we'll call that a wrap.